Are we recording already? About to record. Pause recording. Great. Hello, welcome. Happy Monday, 23rd, week 7. Crazy. Time flies. Um, awesome week this week. I wish that was actually I have a lot to cover in this week, but there's a lot of fun stuff coming in with predictive modeling. So let's just kind of start diving into things. I've got a hard out at 1:30 my time, so at the actual end of this call. Where's your faces? There you are. And luckily, there's only 3 notebooks, so I'm hoping to get through all 3 kind of Jupyter notebooks. But there's a lot of concepts, at least, that I want to also make sure we spend enough time diving into. And then good discussions in the chat so far as well. So thanks for coming back in and helping in the forums. Great to kind of see some real world applications of the content being applied. All right, where should we start? Week
Yeah.
7. Yeah, hey Karen, good to see you.
Hey.
Purpose of week 7, so it's kind of history, kind of where we're coming from, where we're going. Week 5, we introduced kind of the full data science life cycle. So end-to-end data acquisition, data pre-processing, data visualization and exploration with EDA, followed by some like basic modeling. If you remember back in week 5, we introduced the concept of predictive modeling using linear regression, just drawing a line of best fit, but we talked about kind of how this is a foundation for future predictive modeling. Week 6 is a deep dive into visualizations itself, and now week 7 and 8 is going to be a deep dive into machine learning. This week in week 7, we introduced the concepts of regression and classification, which are 2 flavors of supervised machine learning. We'll get into unsupervised a little bit next week, but I'll introduce it today. And then within regression and classification, we got introduced to the linear models that are the foundation of each. So linear regression for a regression problem and logistic regression for a classification problem. Remember, as linear models go, they are both defined by equations rooted in mathematics and history with a strong proof. So again, remember, those are the benefits of linear models. They are very explainable. You can draw a line, you can write an equation out, and you immediately know how you get a prediction. So very explainable and very not compute. I guess they are computationally efficient. What that means is that computers can easily do linear models because people were doing them with paper and pen 120, 200, 300 years ago. 400 years ago? I don't even know. What year are we in now? 2008 still? No. But yeah, anyway, when we start talking about more advanced modeling techniques such as random forest, XGBoost, neural networks, those are going to be more computationally taxing, right? They're harder, they're more difficult for computers to do. And especially when we start getting into complicated neural networks such as convolutional neural networks, recurrent neural networks, your large language models. That's why there's such a boon for NVIDIA chips and these GPUs. And even when we get into this a little bit next week, we'll talk about TPUs, which are like specific, I guess, processing chips for tensors, which is going to be kind of the backbone of many neural networks using kind of matrices as their root, I guess, data input. But that's for a later problem. All you need to know this week, supervised machine learning, regression and classification, linear models. And we also introduced the full machine learning, like I guess, end-to-end pipeline. How do we go from, we talked about this in week 5, but the full like MLOps lifecycle, right? How do we go from data acquisition to machine learning experimentation to model deployment? That's kind of a bad one. And model deployment, model monitoring, all that good stuff. So there's a lot of, yeah, here you go, data source to training data, and then training your model, track your model, different types of models, monitor your models in production, and then retrain your models kind of as you need to. So we'll go through all of this this week as well. Sweet. Let me make sure we have our learning outcomes defined here. There's a couple other ones. Yeah, data scientist versus AI engineer. If you go through the downloads, there's actually really interesting kind of document about that. Again, the data scientist, this is a data science class. You are going to be a unicorn. You're going to be like master of everything. So that's kind of the idea. Remember, we kind of talked about how like there are more specialized roles out there, such as data engineer, BI analyst, well, AI engineer, or typically you'll see this as like ML engineer, machine learning engineer. That's another kind of flavor to this. And typically, those ML AI engineers are going to be tasked with not just the creation of the models, but the deployment, the productionization, and efficient inferencing of that model. Inferencing is just to make predictions. Cool. We'll go through the tools, we'll go through supervised learning and linear modeling. This should be a fun time. I love this stuff. Obviously, kind of predictive modeling was my spike back in the day. I used to work as a ML engineer for a long time. So I used to love kind of teaching all this stuff. So I got my own lecture notes, and if you go creep on my GitHub, I actually created study guides on machine learning for a past boot camp that I used to run. So go check those out. I have a whole thing about what is supervised machine learning, a whole thing on classification because not a lot of people have done much classification in your life usually. And then how do you actually bring machine learning models to production? So we'll try and hit on all three of these today, but definitely not in the depth that I want to. So definitely there's a lot of asynchronous studying that I recommend you do, whether it's with my study guides, whether it's with the Kaggle Learns. Kaggle is obviously going to be great to get a handle on some of this machine learning stuff. Intro to machine learning, intermediate machine learning, and then one that I mentioned in week 5, feature engineering. This is actually going to be unsupervised machine learning. K-means, PCA, more complicated ways of encoding categorical features. So highly recommend kind of this course as well. All right, so let's dive into probably the notebooks and the lecture. Maybe I'll start with some of my own notes here, and then we'll get into the notebooks. Again, my goal is to get through all three notebooks today. But yeah, let's start with some of my notes here. So first, machine learning. What is machine learning, right? So machine learning at the end of the day is just training an algorithm to make predictions based on patterns of some historical data, right? So we want to use patterns to make predictions. And this is just as complicated, even large language models, right? They're basically using predictions of they're using historical patterns to make a prediction. Your very first ChatGPT model, which they've been around since like 2019, fun fact. I think it was like GPT-2 was like open source back in the day, back in like 2019. Let me see if I can find it. From GPT-2. I think it came out in 2019 was the very first one. Yeah, there you go. So if I was more on my game, maybe I should have been investing more in where OpenAI and things were going to go back in 2019. But at the very like basic, like some of these first chat models, all they did was predict the next word. So given that I said I don't know, what's a common, I don't even know why my brain, I was like the lazy dog jumped over, let's see, I don't know. This isn't even like a common saying, but the quick brown fox jumps over the lazy dog. So, like, if I say the quick brown fox, then the model should know that it's predicting that after though that phrase, the quick brown fox, the most common word that comes after that phrase is jumps. So that's kind of what the very basic chat models are doing. They're looking at the tokens you provide. Tokens are the words. They're looking at the words you provide as well as historical patterns. In all of my training data of all the text that this model has read, it sees the word jumps after these tokens X amount of times. So probabilistically, this is the most common word that it wants to predict. So your very first like LLMs, they were just prediction models. They didn't really learn anything. And even now, like the modern like models, they are still using this prediction of historical like text patterns as their root foundation. But this also expands for anything like a linear model, right? If I want to predict the price of a house, then I need to look at historical data. I need to look at comparable houses with comparable size, windows, doors, square footage, use those features to then train a model to then predict what my house is going to sell for. And this is where MLOps also come into play because if I train a model on data from 1997 on house prices, it's not going to be very useful to predict houses today, right? And this is known as data drift. Models trained a few years ago are not going to be relevant for production use cases today when the underlying data patterns may have changed, right? So we want to make sure that we use patterns to make predictions. We want to make sure those patterns are kind of clear and I guess up to date with the real world, right? And that's always going to be a big problem in ML. How do we make sure that our models, how do we understand how our models are going to work in a real world experience and not just in my little black box laboratory on my laptop, right? With machine learning, let me see if I can find my machine learning Venn diagram. Yeah, there we go. I got there's a couple of good Venn diagrams that I like here, and I'll share some of these out a little bit later. Like this is a very basic one, but it's kind of the idea that like machine learning is not like all AI, machine learning is AI, but not all AI is machine learning, I guess, or predictive analytics. So there's some AI that's like AGI, like which is like where we're trying to get with Terminator and stuff. AGI stands for not adjusted gross income. Artificial general intelligence. I was like, I forgot what the A stands. I was like, automated general intelligence, artificial general intelligence. This is kind of where Sam Altman and Google and Claude are all trying to get to. But anyway, we're focused on this yellow circle, which is machine learning. And yeah, maybe this is like a little bit better one. All right, there we go with machine learning inside of it. But anyway, deep learning is neural networks. Neural networks are just one algorithm of machine learning, so that's why it's a smaller bubble. And the data science does everything. Data science also does mathematics, which I like to see in some of these as well. But anyway, within machine learning, I want to like zoom into kind of what we're focusing on, which I guess is this one. Yeah, kind of. With machine learning, know that there are three flavors of machine learning. This is what I want to, where's my little pen here? I guess this one also. But yeah, with machine learning, there's going to be three flavors of machine learning that I need you to learn. So the first is supervised learning. This is where it's going to be spend most of your time. Supervised learning has supervision involved, right? We basically not only provide the data and tell it to find the patterns, but we also give it expectations of historical outputs. And last year, here are the actual prices that houses actually sold for, and I want you to find the pattern of data to target, feature to target. That's where regression and classification is going to fall into. The other second largest branch is going to be unsupervised learning. This is where you provide the data and you tell it to find patterns, but you don't necessarily give it a target. A good use case for unsupervised learning is typically clustering or demographics, right? Here are all of my customers that buy from my website, and I want the model to determine the different demographic clusters within there, right? I don't know who they are. I don't know what they are. I want to identify patterns to identify clusters of information. Other aspects for unsupervised learning, things like dimensionality reduction. One thing you'll find is that if I have 1,000 columns, 1,000 features for my model, it's going to be much harder to identify patterns that are signal in that, right? You think more rows is usually good, but more columns doesn't always lead to better results. So another aspect, and this is where principal component analysis comes into play, we can actually reduce our underlying feature set and go from 1,000 columns to maybe a couple hundred while still maintaining most of the prediction power of those columns. So either way, big idea for unsupervised learning, clustering. How do I cluster and find patterns, as well as feature reduction? And you'll go into both of those next week in week 9. And then finally, reinforcement learning. I love reinforcement learning, but it doesn't have that much applicability into kind of my life, unfortunately. Reinforcement learning is where you like your self-driving cars. We're going to train a car to drive on the road, or your AI plays Pokemon, right? Like you're reinforcing the model with good things. Whenever the model does something good, you give it like a bonus point. And the model's sole purpose in life is to maximize its points and performance. So if you ever see anything, I used to watch a lot of these videos. Where's my pen? Out of my life. Trash, clear all drawings. Great. You could see like AI learns to play Wii Sports. This is like always pretty funny. I'll share some of these videos afterwards, but let's see if I can. Because you'll see that like it's gonna end up. Let's see if I can. Blah blah blah. But like you'll see like it's gonna fail over and over again. And then eventually it'll figure out like how to actually like become a pro and make hits and things. It's kind of funny, but You may have seen this with like AI like plays Go, which was like a big thing at Google. It's like AlphaGo. It was like this came out a few years ago where it beat some like human champions, and this is all trained with AI. This is all reinforcement learning. Whenever the AI does something good or makes a move or makes a play, you give it a reward. And it learns to maximize its reward over thousands of iterations. So notice like this is less pattern training and more like try and do something over and over again until you're successful. So everything you see with the robots that learning how to walk. I don't know if you saw these. These were like crazy, like the robot maids. They were like this like just came out recently. It's like, yeah, it's crazy. Uh, this is all also reinforcement learning. Like it's you've got to train the robot to be able to do specific things. So anyway, reinforcement learning, while really fun, is not applicable usually in our data science life unless you're like doing something based on simulations. But it's still really interesting. Where's my little Venn diagram? So if I go to Scikit-Learn, which hopefully you've been on the Scikit-Learn documentation before, you actually can see this like on here, right? So for scikit-learn, we're going to start with supervised machine learning, classification, and regression. Scikit-learn also supports unsupervised machine learning, clustering, dimensionality reduction, and then also it supports productionalization of models with kind of model selection and pre-processing and full pipelines. So that's kind of like the flow of how this connects. So long story short, machine learning, two flavors, supervised, unsupervised, and then the baby brother of reinforcement learning. Within supervised machine learning, you have two more flavors, regression, predicting a continuous numeric target, classification, predicting the probability of belonging to a specific categorical class. And then under unsupervised, you have clustering, which is find like demographics or find like different clusters of all of my data sets. And then dimensionality reduction, which is kind of a pre-processing step in the fact that we typically do this before training a supervised model, where we want to minimize the number of columns in our data sets. Again, if you get bored, definitely click through the documentation, read up on some of the stuff, and again, we'll do more unsupervised things next week. So, with that out of the way, I want to zoom in on the purpose of week 7, which is supervised machine learning. So, remember, in supervised machine learning, we have two flavors, regression, predicting a continuous variable, and classification, predicting a category. Within supervised machine learning, we're going to end up, yeah, it's like we've already kind of talked about some of this stuff, but we'll start with like a high idea and then we'll get into the ML workflow. So I want to spend the most time here. So first, regression. We talked about the linear model for regression is called like I guess simple linear regression or OLS. Ordinary least squares. This is what I call OLS regression. This is going to be your classic linear model, your line of best fits, all that jazz. With ordinary least squares, with a linear model, where's my notes? You're going to have a couple different flavors. Again, this is all review. We did this in week 5. One feature, one target, y equals mx plus b. Multiple linear regression. This is the most common. You have multiple columns, multiple features, all trying to predict a target. Y equals x1 b1 plus x2 b2 plus x3 b3 plus your constant or whatever, right? So you have your multivariate regression line or multivariate OLS, which is gonna be, or again, we reviewed this all last class too. Whatever your equation is, if I can get the equation. Yeah. Y equals b1 x1 plus b2 x2 plus a constant. So this would if I had two columns to make a prediction, right? Let's see here. We've also talked about polynomial regression. That's where you can add like an x squared, x cubed. Definitely more flexible, but typically underperforms against usual like nonlinear models such as random forests. I never use polynomial regression in my day-to-day. If I have to do nonlinear features, I do a more complicated model instead of linear models. Classification, the model you need to know this week is logistic regression. Logistic regression is super confusing. It has a bad name because while it has regression in the name, It is a classification model. So just keep that clear as well. The one thing to note with the logistic regression, it's still a linear model under the hood. And by that, I mean it has an equation. And that's always going to be the beauty of a linear model, right? Is everything is going to have an equation. And you don't have to know what any of these Greek letters and stuff are, because now we're introducing like the letter E, which is kind of like its own math constant. But whenever you see E and whenever you see kind of division like this, note that this is going to make what's called like a logarithmic curve or an S curve. So you'll see that we actually have our linear model equation as the exponent for the E constant, which is kind of fun. But if we look at what a graph looks like for this, it's going to cause what's called an S curve, which again, maybe we've seen some of this in the real world as well. So the reason why the S curve works so well for predicting probabilities is that it's always going to be bounded, and specifically in the way that the logistic regression equation works, it's bounded between 0 and 1. What that means that it'll either approach 0 or it'll approach 1, but it'll never go above or below either of them. And so now if I'm making a prediction, if I get brought back a probability of 0.99999, whoops, wrong button. How do I share my screen? Then we know that that's likely going to be predicting class one, whatever this class is. If this is a binary classification task, I have two classes, 0 and 1. Yes or no, true or false, whatever. I get a prediction up here, I get a prediction down here, or I could get a prediction in the middle, which means I have less certainty. So the thing about that is that as well. That's what I love about the S curve. If I have two predictions, one for 0.65 and 1.9995, both of those technically are predicting the positive class, the one class. But I have a confidence value now, right? I'm way more confident in the prediction of 0.9995 than I am in the prediction of 0.65, right? So that's why I like to say that categorical prediction is based on probabilities, not just predicting yes or no, because those underlying predictions do matter. And again, your actionability of a prediction or of an inference. Okay, so we've reviewed the two linear models here. Yeah, it's a sigmoid function. If you see sigmoid function, that's just another fancy name for kind of this S curve. It's still a linear model underneath. Common real world problems. Is this customer going to churn? Yes or no? Is this banking transaction fraud? Yes or no? Will a player get injured? Yes or no? Note that most often classification problems are typically going to be binary, so yes or no, one or zero. But sometimes you do have multi-class classification problems, which is I want to predict red, yellow, green. Yes, maybe no, I don't know. Or maybe I have like three or four different categorical of the targets. I unfortunately can't do a deep dive in classification today, but I'm going to try and talk about it as much as I can because it is fairly new to folks. And yeah, with classification models, well, we'll get into them a little bit later. But I definitely recommend like reading up on some of my my guides here because yeah, classification can get pretty complicated as you kind of get more nuanced in the types of problems. Yeah, we won't talk about these algorithms. Yeah, we'll do a deep dive in those algorithms a little bit later. All right, so let's get to the workflow. So the workflow matters way more than just fitting a model. The idea is that we want a framework, right? I want a framework in place. I can then swap out the model, try a bunch of different models, and either way, I can then compare apples to apples, right? So a very common workflow, right? We want to grab our data, we want to train the model, we want to evaluate the model, which is what we're going to spend the most time in today, and then we want to iterate on this, right? We want to repeat it, we want to make sure that it's reusable. We want to minimize overfitting, we want to minimize collinearity, and we want to make sure that our models are most accurate versus our production use case. And yeah, garbage in, garbage out. If your model's bad, you may need to look at your data. If there's no correlations or your data is poor quality, or you've given it too much noise or too much broad like use cases, the models are usually going to be bad there. So yeah, typically a lot of model performance issues comes back to data issues at the end of the day. We don't need to go through all this stuff. So yeah, with evaluation, this is where we're going to spend the most time today. I'm going to do some introduction on this because when you evaluate models, this is kind of the most important part. So let's get to um, evaluation. With regression models, we talked about this in week 5, right? With regression models, we're predicting a continuous variable. So again, your line of best fit. The main way we evaluate these models is what's called the residual, which is the difference between my predicted and my actual value. That residual is what goes into calculating things like R squared, which was the main metric we used in week 5. But the residual is also used to calculate things such as your mean squared error, which is what is my average error? What is the average difference between my observed and prediction, right? Based on the historical data. We also use things like the mean absolute error, which is not squared. We just take the absolute value of the difference versus the prediction. Yeah, and you don't need to get into the weeds of all the different metrics here, but just know that they're all based on the same thing, which is the residual. What is my observed prediction? I observed that this house in 1997 sold for $200,010, but I predicted that house to sell for 198,000. So my residual is, I don't know, $12,000 or something. So everything's kind of based on that error. Just like with anything else, all your metrics have limitations. R squared is typically the one that gets used the most, but has the most limitations. I typically never use R squared in the real world. I use it as kind of like a vibe check when I'm building out a model. R squared doesn't penalize complexity of the model and doesn't necessarily reflect predictive power. It just talks about like variance explained, which is kind of a vague way of like talking about the model. Typically, when I want to make a prediction in the real world and someone goes, Booth, do you trust this model? I need to say, yes, it's going to be within $10,000 95% of the time, right? Plus or minus whatever. And that needs metrics such as MSE and MAE, which is where we're actually getting my average squared error and my average absolute value error. MSE, because it's squared, it does penalize large misses. So if I predict a house to sell for $1 million, but it only sells for like 150K, that's like a large residual. That's a large error. And when you square it, you're going to get a really, really large average squared error in that case. So it's good to kind of be highly penalized when you're really, really wrong. While MAE gives you a more like, I guess, middle of the road evaluation of your predictions. And then usually you generate all the predictions, you generate all the metrics, and you just choose the model with the best of all the metrics, or as many of the metrics as you can. Yeah, my opinion, use R squared in a vacuum as a vibe check. Use MSE and MAE as you compare different algorithms. And then, yeah, if a model is better in all the metrics, then you should be confident that that's the best model. We'll skip over some of the plots and things. And then I guess now I need to jump over to unsupervised. For unsupervised models, this is I'm going to spend a little bit more time on this one because, or for classification models, my bad. For classification models, evaluating them is a lot different. There's no real like residual. Like, sure, I predict this to have like a probability of 65%, and my observation is that yes, it happened or no, it didn't. It's kind of difficult to calculate like a difference there. If you really want to get into things, you can calculate a residual for classification. This is known as Breyer's score, but that's out of scope for today. Instead, where's my GitHub? For a classification model, what we're going to be looking at is what's going to be called our true and false positives, right? True and false negative. You may hear this as type 1 and type 2 error in the real world as well. So you'll see this in the notes for in the class this week. Type 1 and type 2 errors. So this is kind of be where like you take a I'll do COVID because I've done enough. I'm not like I don't want to do pregnancy tests, but we'll do like COVID, right? You take a COVID test and it says you're positive, right? But you don't actually have COVID, right? That's a false positive. The test said you're positive, but that it's wrong, right? You don't have it. So that's going to be one of your type 1 errors, that false positive. A type 2 error is the other way around. You take a COVID test, it says you don't have it, and you actually do, right? That's a false negative. It was negative, but it was wrong, right? So you see this all the time with pregnancy tests too, cancer screenings. You'd want to usually want to minimize false negatives. If I have to tell you in a vacuum which one of these is typically worse, a false negative is almost always worse, right? If I predict that you don't have COVID when you do, like that's a bad time, right? And same thing with pregnancy tests and stuff. And this is actually why COVID tests and pregnancy tests, they tell you to get a second opinion or take a second test because a lot of those tests will actually be built to minimize false negatives at the expense of false positives. It's kind of like a scale. If I'm minimizing my false negatives, I'm going to unfortunately have a little bit more false positive rate. So that's what we're saying. Like, because the models are optimized for false negatives, if I get a COVID test and it comes back positive, there's a decent chance, like a 5% chance, that it's actually a false positive, right? And I should take a second one to really be sure about it. Because the probability of getting two false positives in a row is typically lower than just doing one, right? So same thing kind of with, well, we don't need to get into the detail. I don't care. I was like about to correct me on like they're all independent events and all that shit, but all that stuff. But yeah, either way, typically you're not going to get
We don't
multiple
need the
false positives.
details. The real details are is that you could do a Bayesian thing and realize
Yeah,
that first test is not necessarily that really guarantees that you have the illness, but a second make it more certain.
yeah.
But yeah,
So anyway,
in medicine, I always believe I should err for false positives because
yeah.
yeah, because you can do further assessment. Whereas if you say false negative and you tell somebody, oh, you're fine, but they have cancer, then they come back when it's, at stage 3 or 4 instead of 1.
Exactly. So the way that we kind of talk about type 1 and type 2 errors through mod machine learning models is what's known as a confusion matrix. So there was a couple screenshots that were thrown into the forums this week already, which I love to see. But the confusion matrix is going to give us the exact counts, the exact numbers of true positives, which are I predict yes, and the answer was yes. I predict you have COVID and you do have COVID. That's a true positive. Your true negative, I predict you don't have COVID and you actually don't have COVID. And then what's most important are false positives and false negatives. Note that these are always going to be counts. It's going to look something like this. I've got 165 predictions here. I got 50 predicted true negatives. I got 100 true positives. And then I got 10 false positives and 5 false negatives. So that's we can then calculate like percentages off of that. So anyway, we're going to start with the confusion matrix as our root for evaluating a classification model. And then these counts then turn into metrics. So you may hear things like accuracy, precision, recall, and F1 score. These are our main metrics for classification models, just like MSE, MAE, and R squared are the main metrics for regression models. And again, these are all based off of the the confusion matrix. Your accuracy only looks at your true positives and true negatives. What was my true positive rate plus my true negative rate divided by all my people? So how accurate is your model in actually telling the truth? Accuracy score is usually pretty biased. I like to say that let's say we're training a model to predict if you have COVID or not. I have 100 people, but only 10 of them are actually have COVID. So now I have a model. Let's say my model only predicts that you don't have COVID. It never predicts that anybody has COVID. In that thought exercise, it's going to be right 90 times out of 100 because 90 people don't have COVID. So if I'm right 90 times out of 100, that gives me an accuracy of 90%. And you're like, wow, I've built a great model. But that's actually a really bad model because your model never predicts the negative class. This is known as imbalanced classes. And again, like long story short, I like to think of accuracy score as kind of your R squared. It gives you a vibe check of like how good the model's doing, but you shouldn't actually use it to do or justify model selection. Instead, we want to dive into our false positives and false negatives. The way I like to think about it, precision evaluates false positives, recall evaluates false negatives. So it looks at the proportion of predicted negatives over true negatives, essentially. So again, usually in most use cases, we want to minimize the recall because we want to minimize the number of false negatives in our confusion matrix. But let's say you don't care about one or the other, then we usually go for F1 score, which is averages the precision and the recall. And just to prove this, you can see that the precision is going to be, where's my graph? Yeah, your recall is your true positives divided by your true positives plus false negatives. And then your precision is going to be the opposite of that. Your true positives divided by your true positives plus false positives. And then all of this is going to be released in what's called a classification report that we're then going to generate when we talk about classification. So, the listeners amongst you may have noticed that I did not talk about probability at all. And that is the problem here with your true and false positive rates and your confusion matrices. They only look at counts, right? Even if I predict the COVID test to be 0.65, 65%, that's still going to fall as a yes. Like I predict it's above 50%, so I predict you do have COVID. So how do we turn some of those probabilities and confidence? How do we use those probabilities to help evaluate our model? That's where the rock curve is going to come into play here. The rock curve usually uses probability. It utilizes probabilities in its interpretation. So it's going to create a graph and provide a metric called AUC, area under curve. And again, because it's based on probabilities, this gives us a little bit more of a sense of how good our models is. Usually in a vacuum, I actually use AUC as my metric of choice when comparing classification models because it does use that probability. But then I use the confusion matrix as kind of a way just so I fully understand my model performance here. But yeah, long story short, you typically want the rock curve to be close to one, and you get this like perfect little S curve. Again, the rock curve is out of scope for this week as well, so don't feel like you need to know it. Same with Briar scores, and you can read up on this on your own time. Big things you need to get out of week 7. Regression versus classification, linear models, OLS versus logistic, and then evaluation, mean squared error and MAE versus your true and false positive rates for classification. That's really what I want to get out of this week. And then yeah, the same processing flow is going to happen regardless of your model problem. We're going to get our data, clean it up, do any scaling, do any encoding, any imputation. That should all be recap from week 5. We want to choose our features. We want to see if there's correlations. We want to minimize multicollinearity and want to make sure we understand the features that we're using. We then split our data into train test sets, and then we do our ML experimentation, train an assortment of algorithms, generate metrics such as test precision recall, check everything against each other, and then kind of choose the best feature. Again, my usually recommendation is you want to always go with the more explainable and less complex model as long as it meets your SLAs in terms of performance. And then make sure you understand why the model is making the predictions it is, at least to the best of your ability. Cool. And let's actually see this in action. I want to get through all my notebooks by 1:30.
Well, actually, a lot of this is actually in the next module.
Yeah. Yeah, like week 8, we
Good
introduce
good
tree.
preview here.
Yeah, well, week 8 is a crazy week. Week 7 is like the combo, like the calmer of the two ML weeks. Because week 8, we also do unsupervised clustering, dimensionality reduction, as well as random forests, as well as classification. It's kind of a really heavy week.
And more
So
about evaluation there
yeah,
too. Well,
yeah, hopefully,
I think the pattern they have is that it's you have a really heavy week and then you have a lighter week and then a really heavy week and then a lighter week.
yeah.
Maybe that's by design. Maybe that way people could be catching up with the heavier one and not be overwhelmed with the lighter one.
Yeah, I think I should have enough time to get through all 3 notebooks here. But yeah, just kind of go through. I'm starting with the first notebook, which is 732. And again, just a quick rundown of our tools. We're going to be using a lot of Pandas. We're going to be using a lot of NumPy. We're going to be using a lot of Scikit-Learn. Once our data is in a data frame, you'll see that we're going to be able to really easily integrate with machine learning models. And the reason why we love Scikit-Learn, Scikit-Learn has a whole bunch of algorithms already kind of boosted there. So we talked about how like the idea is to build a framework so then we can use different models. And you can see like just for linear models, we talked about OLS, but maybe I talked about this in week 5. You also have Ridge, Lasso, Elastic Net. Those all count as linear models because they're based on equations. But then we also have support vector machines for regression problems as well as classification problems, nearest neighbors for regression, naive Bayes, your decision trees, your gradient boosted trees, random forests. Like all of these are different algorithms we can use. Neural networks, right? All of these are different algorithms that we can use to test the problem. So this is why when we think about machine learning, we should be more concerned with the framework. How do I clean and prepare the data? How do I evaluate the model performance? And then the algorithm itself is just like a Lego brick. We just plug and play different models, but the rest of the framework or pipeline kind of stays the same. And next week we'll walk through kind of what that actually looks like with a full pipeline. All right, so let's just do our like warm up here. This is just kind of a quick review of OLS or simple linear regression. Here's my data set. We have a lot of data set about cars, and we want to end up predicting something like the fuel efficiency of the car. One thing that's worth noting, let's first do a df.info. A lot of my data here is going to be categorical. Make, model, vehicle class, transmission, fuel type. So remember that this idea of encoding, we have to somehow turn these categorical variables into numbers, whether it's with one-hot encoding or dummies, PD get dummies, or we use something like label or target encoding or other ways to deal with that. But I am happy that I have no missing values, which is great. So let's look at our numeric correlations. We can do see if I want to predict something like the fuel consumption on the highway. We do have some strong correlations with like energy size and cylinders, which again kind of makes sense. If you have bigger engines, I probably expect you to like be have worse fuel efficiency. Yeah, there you go. The fuel consumption combined miles per gallon. So I have like a negative fuel efficiency depending on the size of my engine. And I think CO2 emissions also make sense to me. So again, from our data, we can see that we have some outliers and we have some interesting correlations here. Cool. We can do some exploratory data analysis, which I'm just going to whiz through. Again, all I'm looking for here is are we mostly normally distributed? Are there any crazy outliers? All this data looks fairly good to me. I'm looking at the linear regression. I'm looking at the fuel consumption versus CO2 emissions. We can see there's some strong linearity here. And same thing with whatever this is, engine size versus CO2 emission. I'm not sure why they restricted this to 0 to 27, but whatever. Scatter plots, and let's actually do a regression. So now here's the problem that I want to solve. I want to predict the CO2 emissions using engine size. And so again, if I go back to my correlations, we can see that the CO2 emissions has a very strong positive correlation to engine size. So we should be able to use one to predict the other fairly well. And same thing, we do a CDF dot plot kind equals scatter, and then X equals engine size, and Y equals CO2 emissions. Hopefully There we go. Split.show. Cool. So we can see that I should be able to draw a line of best fit here that should be pretty good, right? So that's my plan. Oh my God, my annotations. Cool. Whoops. Annotations out of my life. All right, so first thing we're going to do, now that we've selected our feature selection and we have our target, we want to split our data into training and test. We train the model on the training set and then evaluate the model, calculate our MSCs and stuff on the testing set. And so let's go ahead and do that. We can see that we're going to train our model on 853 rows and evaluate our model on 214 rows. Let's train a model. I'm just grabbing a linear regression from Scikit-Learn, and we can see that my equation is y equals 39 times the engine size plus 126. So we have a very basic model here. We have our line of best fit that can be drawn within it. So now let's get to the most important part, the model evaluation. Notice here we have our description of our big four. Mean absolute error uses the absolute value of the residual. Your MSE, which is the squared residual. Your RMSE, which is the square root of the MSE. Basically, it gives you a number that's at the same scale as your target. And then R squared uses explains the percent of variance explained by the model. But again, it's only useful in like a vacuum. So notice that we're just importing all of these from the metrics, and we can quickly calculate the MAE, MSE, and the R squared. And you'll see here that the R squared lines up as just the square of the correlation. This 874154 comes from this correlation value right here. So R squared literally is just the correlation squared. But what's important here is evaluating these numbers. So let's actually just run through this. Mean absolute error 2410. On average, my prediction is off by 24 points of whatever the CO2 emission is. But my average squared error is 31. This is interesting to me because it also indicates that we had a couple of large misses. Remember, a large miss will increase your MSE and therefore also increase your MSE. So this is actually interesting. It looks like we had a couple of bad outliers that skewed our predictions, but either way, like the number, if you had to hold a gun to my head and be like, how good is your model? Like, yeah, we're off between 24 and 30 points for each of the predictions. So that's good to know. That's actually pretty small, I think, given this. I think the other one that I wanted us to do was to look at what did I want was my X fuel consumption, and I guess we still want to predict whatever I'm just gonna do it up here. Let's change this to fuel consumption. And somebody remember these numbers. Maybe I'll get a little snip. Boop, boop, boop. I'm just stealing these numbers. Oh no. My kernel, I hate these notebooks. They got mad at me for doing too much. Womp womp. What I get for trying to do too much here. Either way, I think that's kind of a fair, kind of good start. Kernel status idle. Sweet. I think it died though, so we need to rerun it. Run all cells. Yay, it's back alive again. All right, so if I go, did I swap it out? I didn't. So let's swap this out for what's the one I want to do? Fuel consumption. Let's steal that column. So all I'm doing here is I swapped out my feature set. And as you see, as we change our feature set, we're going to end up with a different model with different evaluations, right? So one thing to notice is that with this new feature, the fuel consumption, my R squared is higher. And if I compare this to my old metrics, my MAE is lower, my RMSC is lower, my MSC is lower. That's all good sign. I have less error. So just by swapping the feature, I was able to make a better model. And this comes back to my overall point of feature selection is honestly the most important part of training the model. If you have bad features, bad data sets, that's really going to impact how the model performs. And again, this is the same model algorithm. It's the same, just simple linear model. So the big idea is that, great, this is a good place to start, but we usually want to move this into a more complicated algorithm. So again, most of the time, we want to use more than one column to predict a target. This is known as multi-linear regression or multiple linear regression. So let me go ahead and I think I'm actually gonna try and show a full end to end here for this one. Let's see if I can do it. All right, so we're gonna use the same data set, which is that we want to predict cars. Yeah, that's fine. We'll do it in this notebook. I kind of wanted to make a new one, but it's fine. Cool. So we're going to be predicting cars. Note that we want to fully evaluate everything. We're looking at our categorical columns here. We've talked a lot about the art in encoding these categorical columns. I think in our example, we literally just drop all of them, which is fine, but rip. I think that you can probably make some predictions using kind of the make and model of the car, but I think the idea is that there's going to be some multi-correlation with things like the engine size. If I know you're driving a giant truck, you're probably going to have a giant engine. So looking at our metrics here, I'm just looking at the correlations again between things. We see there's a decent amount of multi-correlation. Again, the bigger engine, the bigger cylinder, the more that's going to correlate to your fuel consumption and your CO2 emissions. So here, I wonder what it's going to have us use as our feature set. Oh my God, it didn't even tell me. Anyway, let's just run through some more EDA. Yeah, I was going to say that's kind of a bad one because which is not found in Axis. Oh, we already did. Cylinders. I want to make sure I know what I'm doing here. df.head. Oh yeah, they're already gone. I already ran it, I guess. Vehicle class, engine size, fuel consumption, CO2 emissions. And then we're bringing in vehicle class here as well. Or we're getting rid of that. Cool. So let's see what we want to predict. In my opinion, both fuel consumption and CO2 emissions should be targets. But if I look at my pair plot, we can see again the histogram and strong correlation between all of our features, which is great. And I love me a good Seaborn pair plot graph. Yeah, and one thing to kind of highlight here, this is good that the notes call this out. The relationship between fuel consumption and CO2 emissions is non-linear, right? It's like a curve here. So this implies that maybe a linear model won't be the best model to do. So either way, we have our feature set here. It looks like I know what we're doing. X is going to be our engine size and fuel consumption, and our target is going to be CO2 emissions. So knowing my fuel consumption and knowing my engine size, I want to be able to predict the amount of CO2 emissions coming out. So this is where we can start doing our full, I guess, pipeline or pre-processing. I want to scale my numeric features. And if we look at kind of what this looks like and why we need to do our scaling, remember what our scaling does. Oh my God, I forgot I need to wrap it in a pd.data frame. What this does is that it takes again, 0 here is going to be, I hate that it dropped our feature names. We don't need to do this whole to NumPy nonsense. Sorry, I'm changing the lecture code. Um, It still lost my feature names, I guess because of the standard scaling. But either 0 is going to be the engine size and 1 is going to be the miles per gallon. So you'll see that without, what do I know? What's the story I want to tell here? X dot describe. The story that I want to tell is that if I just have engine size and fuel consumption, notice their scales are off, right? We go from 1 to 8 as my range for engine size, while for miles per gallon, I go from 11 to 60. That can confuse models, especially when I have crazy differences in my ranges. So by scaling our features to be on the same range, that typically is easier for the model to find patterns in. So you'll see here, after I've run this through my scaler, both my engine size and miles per gallon are both going to be on a range of about -2 to +5, which again kind of makes sense if you think about your standard deviations. So either way, we've standardized our features to be having the same range, which usually is helpful in helping a model identify stronger signal. So that's the big idea with the scaler. Now that we've done our scaler, I was gonna say they should have done the scaler after the train test split because now we have some leakage in the test set. But it's fine. I guess for example, we now have a multiple linear regression and we can calculate our metrics off of that. Yeah, I was gonna say, what are we trying to do here? Maybe I should bring back my dot NumPy. I wish I had one of my, I'm gonna probably go off script and choose one of my uh, coding examples here in a minute. Maybe we can ask ChatGPT to generate something for me. But if we look at our graphs, you'll see that with my multilinear regression, we're pretty good here. We have a 3D graph that typically means nothing. Again, these aren't the plots that I would generate. I want to know, where's my evaluation? Oh, good job, Pass Alexander. I did do this for my last boot camp. All right. I'm ignoring everything we talked about above. Let's actually get this into the real world. What does this actually look like? So in the real world, let's go back to our original data frame. I have vehicle class, I have engine size, fuel consumption, and CO2 emissions. Good job, past me, for doing this last class. If I look at my data here, we'll see that there's some correlations. There's definitely some differences in the ranges. So we need to do a few things. Again, this is always what we talk about on the data cleaning side. First, do I have any null values or have to do any imputation? The answer to that is no, I do not have any null values, so no imputation is needed. Do I need to do scaling? Yes, we need to scale our numeric features so they are on the same range because this is not on the same range. And then finally, for completeness here, do I need to do any encoding? And yes, I do need to do encoding because we have a categorical column here called vehicle class, which is going to be a categorical column. We can see we have all of these categories or types of cars. So the plan is we're going to use a pipeline, which is a scikit-learn object to bundle everything in together to make it easy to plug and play different algorithms. So here's what a typical pipeline looks like. For my numeric features, right, which are going to be fuel consumption and engine size, I'm going to impute them as needed and then scale them using the standard scaler as we demonstrated above. For my categorical features, I'm going to impute them as needed with the mode, the most frequent, and then use a one-hot encoder or a get dummies to do my converting to numbers. Then we can combine both of these together into one column transformer. God, this is beautiful. Good job, past me. So in total, what my preprocessor does, it takes my columns, does the imputation, scaling, and encoding as needed, and returns an object that's ripe for machine learning. Then, because we're doing a regression problem here, I have a custom function that I wrote to evaluate the model just based on the algorithm. And it doesn't matter what the algorithm is, we're just gonna train our model and call it a day. So you're gonna notice we have the same pre-processing pipeline defined above. We can then define our model as do this preprocessor and then insert your algorithm here, train the model, generate your predictions, calculate your metrics, and then from there generate a couple plots. I think I generate the predicted versus actual plot just to make sure that we can tell how our model looks like. Oh, I love it. I'm so glad I did this in my last boot camp. All right, so let's actually see what this looks like in the real world. So let's actually do our kind of plan here. My goal is I want to predict CO2 emissions. We're going to do our train test split. And then here's the important part. We're going to use this algorithm and we're going to evaluate the linear regression. And this is kind of what I wanted to see here. So we're going to be using three input features. Our input features are going to be our engine size, vehicle class, and fuel consumption. And again, we're predicting CO2 emissions. So let's highlight a couple things here. The first things I look at is the test metrics, specifically the test R squared. This gives me my vibe check. So we have a strong R squared here of 0.91. So that's great. We seem to be pretty good at predicting on the test set. Next thing I'm going to look at is overfitting. Overfitting is when a model identifies patterns in the training set that doesn't exist in the test set. Again, we talked about that in week 5. To evaluate overfitting, what I do is I compare the metrics of the training set to the metrics of the testing set. So if the model is better at the training set, it's going to have much better metrics, right? So if I compare the metrics, MAE 14 to 13, MSE 406 to 351, R squared 89 to 91, these are all fairly close. So to me, what this implies is that there is no overfitting. The model is not better at the training set than the testing set. It's about the same performance on both training and test, which is good. You don't want overfitting because overfitting implies a poor performance in the real world. And then the last thing I look at is this predicted versus actual plot. This is a plot of my residuals. If I see some crazy dots like this, I can immediately tell that this may be an outlier. This is a pretty bad prediction. I would predict this to be like on the line here, and it actually is like way lower, right? So that's like a bad sign. On the testing set, that's kind of where I care about this the most. I can see we have kind of a relatively poor performance on these higher. I'm consistently under predicting these high actual emissions. So this is a problem. I'm already identifying a pattern here of a limitation of my model. And if I had to guess, the answer is probably just going to be like I don't have a lot of cars in my training data that has a lot of high CO2 emissions. So because I have a lack of data of this small pattern, my model is not predicting it well. But for the most part, my model is predicting everything else fairly well. So that's good. I would just say that if you have a car, maybe like your super double lifted truck, it's probably not doing well, and it's not going to be able to predict it as well as you probably would think. So, that's kind of why it's important to look at all aspects of your model in a well-rounded way. Again, I like to say that like again, all models are wrong, but some are useful. It'll take me back to week 1 or week 2. So same idea here, right? I'm always very pessimistic. Where is my model wrong? Where should I be worried in the real world about someone making a decision off of a poor prediction, right? Again, you also hear this as like extrapolating beyond the model. If my training data is only up to houses that cost $600,000 and I want to know how big my $1 million mansion's gonna like sell for, I shouldn't extrapolate beyond my training size. And that's kind of what we're seeing a little bit here, right? Is that unfortunately, I think that my test tech a little bit unlucky in some of these cars. We just don't have a lot of cars with this high CO2 emissions. So it's almost like I'm extrapolating beyond what the model's been trained on. My model's been trained on a majority of cars less than 400 in terms of CO2. So using it beyond that, I would have a worry. And so if I did deploy this model to production, that's what I would say. Be be wary if you are trying to predict a high CO2 emitting car, as that is almost extrapolating beyond the underlying training set of the model. Anyway, the second big idea to get across is that the algorithm should be a plug and play. Right now that I have my framework of what I want to do with my algorithm, with my pre-processing and my model training, I can just swap in a million different algorithms to see which one's best. So let's plug in a lasso model. You don't even need to know what a lasso model does, but you can just plug it in and you can see we have different metrics and different performance than the linear regression. So this is interesting. Wow, I'm excited, so exciting. Notice that my model is a little bit worse. R squared of 8.9, that's lower, but I usually like looking at these ones. MAE of 14 compared to the MAE of 13, MSE of 451 compared to an MSE of 351. So this model is worse objectively. Second, I'm looking for overfitting. No overfitting because it has the same training and test metrics. And then finally, I look at the graphs. Where's my model bad? My model is bad still at predicting high CO2 cars, but also we have some like weird missed over predictions here. I predicted to be 300, but actually 250. So that's kind of sus. Or that's kind of sketch out of my life. Inbox message. So my lasso is worse. Let's try a ridge model. My ridge model is about as performant as my logistic regression. Let's take the MSC MAE 353.13 compared to a 351.13. So it's still slightly worse than my linear regression. So womp womp. My linear regression is still the best. This is called your model tracking, or you're tracking the evaluation metrics of multiple algorithms. And finally, just for completeness, let's plug and play a complex algorithm, a tree-based one that we'll dive into next week, a random forest. And we should be really interesting here. Yes, I love it. I love it. I love it. Let's talk about this. This should be throwing some red flags at y'all, just straight off the top here. So why are we throwing the red flags here with our random forest? Well, let's just walk through it. So first thing we're going to do, what's the kind of in a vacuum? How good is this model? R squared of 98. Wow, we did it. We made a great model. Yay. Second, let's check for overfitting. Do we have overfitting in this model? I would argue and say yes, we do have overfitting in the model. My train MAE is lower, so we're better on the training set in all the metrics. So my random forest is better on the training set, which implies there's a little bit of overfitting here. This isn't egregious, mostly because my model is pretty good, but there's still overfitting. And then where is the limitations on the testing set? This is where you can also see a little bit of overfitting. We kind of get these sporadic dots that you don't usually have in the training set, which kind of indicates some of that overfitting. But for the most part, it's pretty good. And we're even able to predict those high carbon efficient cars too. So I would say this random forest is the better model. And we probably could have gone in knowing that this is the case. And if you rewind all the way back up, you'll remember that we even discussed a non-linear relationship between fuel consumption and CO2 emissions. Linear models, by definition, only track linear relationships. So I probably should have been an indication to me that I needed to use a tree-based algorithm or a polynomial regression to capture those non-linear effects. Yeah, that's the importance of the pair plot. So I'm not surprised the random forest performed best. But again, big idea of what I want to get across on an end-to-end machine learning lifecycle. The framework, the data processing, and the data evaluation is what matters the most, and then plug and play the algorithms. Sorry, I got my window open. You can always learn like what the algorithms are more in depth, but if you don't have a good framework in place, you're not going to be able to train good models. I'm gonna jump straight into again. Please ask questions in chat to give Karen something to do. I'm gonna jump straight just for the sake of time. I'm gonna jump straight into the classification notebook. Note that the classification notebook is going to be very similar to kind of what we're doing here. We're going to have the exact same pre-processing steps. Just note that the evaluation is going to be different because we're going to be using our confusion matrix and type 1 and type 2 errors, but the philosophy is exactly the same. Please tell me I did the same thing back in the day. Oh, great job, past Alexander. I did so good. Good job, past me. So let's fly through and we can see what this looks like. And I'll make sure these notebooks are shoved into my GitHub after class today in the live session folder. Because yeah, this function here, this like make evaluation or make regression, like you can just rip this, put it in your own pipelines. The only thing you need to change is like what are your numeric features and what are your categorical features that you want to like impute or encode or scale or something. And anyway, kind of what this is looking like. I think I showed you this picture in week 5. The reason why you should learn to love the pipeline is because it standardizes how a model like looks. This is kind of what's happening, right? We have my numeric features, my categorical features. We train the model, and then you output your thing. And then if we actually look at, I'll post this in the chat. Scikit-Learn limit pitfalls. I'll put this in our forum after class. Um, the common pitfalls with training a model, you're gonna have things like inconsistent pre-processing, data leakage, which is actually what was happening in the simple linear regression notebook. And then how do we avoid all of this stuff? And it's like use a pipeline. If we get to the bottom, we're dinner recommendations. Use a pipeline. Whoever like it wants us to do that. So. Interesting stuff. Yeah, you'll hear it. They use a pipeline to prevent data leakage and all that good stuff. Anyway, we'll leave that as an exercise for the reader to explore more. All right, so first what I want to get through with this notebook, what does a logistic regression kind of problem look like? And what does an evaluation of it look like as well? So here I want to predict whether or not a customer, this is a classic customer churn data set. I have about 200 rows here. Let's do a .info. And so my target is going to be, yeah, we have 200 rows. My target is going to be this churn, whether or not someone has churned or not. And I have all these other columns here to help make that prediction. Looking at my data here, you should feel pretty happy. I have no missing values and everything is a number. So I don't need any imputation and I don't even need any encoders. So you got a really easy data set here, which again, is by design. But let's take a quick look. Let's check to see if there's any correlations. Correlations don't always matter as much for classification models, but they can still be helpful. So here I'm looking at the correlations to my churn column, and I do see that there's a few here. Let's do a quick gut check. How long they've been tenured and employed makes sense. The longer you've been there, I don't know, maybe that does have a relationship with churn. Um, and then I don't know what some of the other ones are, like how long you're waiting for on the call and stuff, your income level. Maybe those should have less of an impact on churn. So anyway, I'm just going to do feature selection based on my correlation analysis. I want to use these columns. And again, this is an art, not a science. So go back in and try new columns or trust your gut, talk to your domain experts. Feature selection is going to be more important than the model choice, as you'll see kind of in the real world. And again, notice that we're going to use tenure, age, address, income, education, employment, equipment to predict churn. So same dealio, get our training data, get your testing data, again, your scaling should happen after the train test split. You got prime data leakage here. But again, for completeness, we've scaled our numeric features, we've split our data into training and testing sets, and we can fit a model. Let's fit a logistic regression. We can see that my logistic regression is going to predict my target classes, but in reality, it's predicting probabilities. So for this first one, it predicted a 0, they're not going to churn, but it had a probability of 75%. Contrast that to the second one, which also predicted not churn, but it's much more confident. It's predicting that 0.92, right? So it's 92% more confident that you're not going to churn. The only one that does predict to be churned is this last one, which actually came back with a probability of 73% likely to be churned. So, and the reason why I like showing this is know that a classification model does two things at the same time. It predicts the probability of belonging to a class, which then, by definition, gets mapped to predicting the class itself. But underneath your classification prediction is always going to be a probability. Also for proof, We can grab well, like the coefficients. And again, I like just showing that like behind the scenes, there is a mathematical equation. You can plug these coefficients in on your TI-85 calculator, and you can show your boss this is why you're getting the prediction that you are. However, after you scale, you can use the coefficients both for logistic and linear regression. The coefficients can be used as a somewhat like importance metric. So we can see here that equipment and tenure, they seem to have the most importance in my equation because their coefficients are larger. Again, this is not always going to be the case. Typically, this you can only use coefficient size for scaled numeric features. But again, that's like beyond the scope of this class. I just want to show here that my feature selection matters. I probably didn't need to include income. It has a very small coefficient. And if you remember, income has a very low correlation with my target. So I probably shouldn't have included income as a feature in my model. That's kind of what I want to relay here. Again, like feature selection, it's an art. But let's get down to calculating performance. There's a lot of different metrics we can use to calculate the performance of a classification model. One is log loss. This is kind of like a lot of people like log loss. I like this more for neural networks. So I'm going to kind of gloss over it and we'll go into kind of the main ones here, which is our confusion matrix and classification report. This is going to tie back to what we discussed at the start of the lecture, where here's my classification report. And there's some things that immediately jump out to me. So remember, this should be our true negatives, true positives, false negatives, false positives, something like that. We can look at the numbers. Anyway, we only have what, 40? 40 rows. We have 40 rows. We predicted 25 of them not to churn. We predicted four of them to churn. We did not predict any false positives, which is I predict you to churn, then you didn't. But we did have 11 false negatives of people that did churn that we predicted to not churn. So that's not great. We can evaluate this on my classification report here. Let me pull up my little calculator. So let's see if we can actually calculate these numbers. Um, let's do precision on well, I want like overall precision, but my overall rate here, we have 25 divided by 40, which should give me my 62. No, that's 36 divided by 40. It's like gonna give me my 82 number or 30. What am I doing here? That's because this is by 0 and 1 class. I don't have time to pull up the actual equation, but these numbers do map to these numbers here. I was gonna say, I wish yeah, we had 15. Okay, here we go. Let's get this recall number of 0.27. We had 15 people that churned in my test set. Of those, we only predicted four to actually churn. So 4 divided by 15 should be my 27 number. Yay. So that's my 0.27. Same thing for the 69 number. It should be the vertical column here. So my precision for the here, we had 25 people that we predicted to churn, that predicted to not churn out of 36 total not churn predictions, which gives me my 69 number. Sweet. So either way, the way I would break this down is we look at our false positives, which is precision, versus our false negatives, which is recall. And again, what stands out to me is this 0.27 number, which means we have some high false negatives in my one class or in my churned class, which again, we can see down here below. 15 people that actually churned, we only predicted four of them to churn. So we had 11 false negatives, which is a bad sign. So I would say this is a poor model because I want to prioritize that false negatives. I want to minimize my false negatives, which we haven't done here. Note that my overall accuracy, though, is 72%, which doesn't necessarily reflect the whole performance of the model itself, right? That 72% is biased because we got 25 true negatives of people that didn't churn that actually didn't, which kind of dominates that performance. That's why we have zero false negatives for my not churning class. So anyway, big idea is to take apart from type 1 and type 2 evaluation. Your accuracy score is usually biased. You typically want to look at a little bit deeper, go into your false positives and false negatives. Even if it's just a lot of numbers thrown at you, look for things that immediately jump in your face. Typically, having a low recall or having like a poor performance in your false negatives is usually going to be a red flag. So let's see this with a more robust example. Um, Here we go. I think this is where here we go. All right, here's the like you're changing your columns here. So basically it wants to know like how does changing the columns change the predictions? And you can see that like by adding in wireless, it does help the model. Where does wireless? Yeah. Adding in wireless, uh, it does help the model. Oh my God. My log loss is improved and actually it's made kind of a worse model. Yeah, I now have five false positives, and I haven't improved my false negatives at all. What if we remove equip? Same thing, no benefit to my false negatives. And what if we remove income and employment? Still no improvement to my false negatives. So I would say that the columns just don't matter here. All right, so let's actually see this all the way through. Let's create our same function that we did for regression. We're going to have a pipeline. Again, my pipeline is going to look very similar to the regression one if my frickin' kernel would stop refreshing. So you'll see for my numeric features, we're going to impute them using the average and then scale them with a standard scaler. Categorical, impute them with a mode, encode them with one-hot encoding, transform all my columns, and then calculate the metrics. One thing to notice is that because I have zero categorical features, I just left it as an empty list. But this still provides me the flexibility of adding in categorical features in the future to this model. Only other thing that's different, again, we calculate our metrics, but they're different for classification. I'm going to print out the accuracy score, F1 score, and log loss. And then we also are going to print out the classification report and confusion matrix for the test set. So I'm using these accuracy score and F1 score and log loss to check for overfitting, and then the confusion matrix and classification report to understand the limitations of my model. And then we'll make a plot of the confusion matrix and we'll make a plot of the rock curve as a bonus. So we only got two algorithms to check here. First is the logistic regression. Wow, we spot on time. I think we are. So hopefully this doesn't crash my kernel. Yay, magic. So let's first check for like how good is this model in a vacuum? And like we have the accuracy score of 0.78, so like it's fine, I guess. Let's check for overfitting. Overfitting, I'm gonna have very similar number. I'm gonna have different numbers between my training and test set. That doesn't seem to be the case here. These are fairly close to each other. So there's no overfitting, which is good. And then how does my model look in a vacuum or how does my model work in production? Not great. Not great. So a couple things I'm looking at. Again, my recall is not great and neither is my precision. So I have lots of false positives and false negatives in my predictions of the churn class, which we can see in my confusion matrix. Of nine people that churned, we only got four of them. Wait, no, how many people churned here? Nine. Yeah, so we have five false negatives and four false positives, which are not great. That kind of ruins, especially with the low sample size that we have here. So not great. And you can see the full pipeline and you can see my confusion report. My rock curve, it doesn't look that great either. Again, what a good rock curve should look like based on the probabilities is going like straight up and then straight this way to maximize the area. So this is like fine, but it's a little bit too jagged. And I like my awk higher up, like in the 90s, if I had to make a strong opinion on something. So let's try and compare it to our random forest, which again is just a more complicated model. And this should jump out to you. There's some exciting things that are happening here. With my random forest, first thing to note is Overfitting. Wow. Again, this is a very common problem for tree based on exotic models. My metrics are pretty different going from my training to my test set. So similar to what we saw in the linear regression. My training accuracy and training F1 score are perfect. I'm getting perfect predictions on my training set, which is wild. You should never see perfect predictions anywhere. And my log loss is almost perfect. Log loss you want down to zero. As closer to zero is better. Um, Looking at my testing metrics though, like they're not nearly that close. So what this implies to me is that my model has found patterns in the training set that don't exist in the test set. Now let's look at the confusion matrix, and it's worse. We have one more false negative than the logistic regression. My recall, this is what I always kind of go to though, always. I always look at the recall. My false negative rate is worse than the logistic regression. So the random forest overfits and has worse performance, especially on false negatives. So, and my awk is lower as well. Again, awk you want closer to one. So my rock curve is worse. So with the random forest, I have a worse model, worse metrics, worse probabilities. So I would again choose that the logistic regression is the better algorithm here. And then why I like highlighting this as well is a more complicated algorithm will not always give you a better model, right? The logistic regression, the linear model, outperformed the more complicated tree-based random forest model on this data set. And again, the other part of this example specifically is that the column selection really drives home I guess, the performance of the model here as well. If I had more time, I would definitely iterate on this. I would try different assortment of columns. I would try different algorithms. There's ways that you can also have your tree-based model to minimize performance. But at the end of the day, the problem with this model is the data set. I can't believe nobody called this out at the start of the notebook, but we only have 200 rows. And of those 200 rows, only 58 of them are people that have churned. That is what we call as a small sample size. It's going to be really difficult to train a model with signal to predict that low target count. Typically, especially as we get into tree-based models, we need thousands of records. And especially if we have a classification, I want that to be close to a 50-50 split. I want to see 50% churn and 50% then not churn, just so my model understands what's going on. My model is biased here, and that most of my people don't churn. And it's only got a limited slice to find patterns of people that did churn. So again, there's ways and techniques around this, especially if you start reading some of my notes, you'll see things that we have like smote samplers or smote sampling, and like different ways to resample your data to try and get to that 50-50 split. But off the cuff, I should have already known that this was going to be a poor model, right? So if I was in the real world, I would go back and say, hey, let's acquire more data here. I would love to get some more observations, specifically of people that did churn, and then we can build a real production model off of that. Last thing just to leave you all with, because I have to hop to another call. Once you've chosen your model, that's known as model selection, right? So again, they talked about this with a little bit with Scikit-Learn here. If I choose the logistic regression, that's where I can start doing a grid search, hyperparameter tuning, and then we can get into model deployment. Specifically in machine learning, it's going to be saving your model as a binary file. So I like to call it pickling because you use a library called pickle. So it's where you convert a model into a binary object, and then you can pass that binary object to an API deployed on some virtual machine or something else. And we'll try and get into this over the next couple weeks in terms of the deployment cycle, because that's when you can start thinking about batch inference, which is every night at 2 a.m. I'm going to grab all the customers that I saw yesterday. I'm going to read in my pickled machine learning model and make a batch prediction for the probability of who's going to churn or not. Or you could do something like a streaming inference, which is I have the model deployed to an API endpoint and I have a data pipeline going back to week 3 or 4 here. Every time a new customer logs onto my site, that immediately sends a request to the API with just that one customer. my model through the API makes its prediction and returns the one prediction back, right? So this is known as like ad hoc inference or streaming inference. I'm making my predictions one at a time live during my like normal data pipelines versus batch where I make multiple predictions at once, typically overnight at 2 a.m. And again, it's typically related to how you've designed your data pipelines. Because if all your data pipelines are batched, like every night at 2 a.m., I'm going to get all the data anyway, then it doesn't really make sense to deploy your model as an API endpoint. And if you're curious on this, let me see if there's a diagram. Um, like there's different ways to do kind of this model serving. This is not what I wanted, but it's close enough. Yeah, I wanted to see if there was an image here. I guess there's not. But I'll send out some links about some of this stuff. But it's basically like how do you deploy machine learning models for again this idea of real time and batch serving and inference. And then it's typically done through APIs, right? You can create an API to host your model. Last thing just to note on this, obviously with your model, you're gonna have a lot of dependencies. Oh my God, this freaking pop-up. So remember at the top here, we installed like specific versions of all these libraries. I want to make sure that my model environment where I'm making the predictions reflects the libraries and the versions that was used to train the model. So this is a common pitfall. I train a model on Scikit-Learn 1.6, but I serve it in an environment that only has Scikit-Learn 1.4. Or maybe it's an updated environment that's running Scikit-Learn 2.1 or something. That's going to cause my model to break because of library dependency mismatch. So the other thing to think about, and again, if you read my production ML document, I talk about this idea of containerization, which is how do we make a lightweight container, a bubble that has not just the model artifact, that byte object, but also the libraries it needs, right? With the correct versions that it needs to be able to support the correct, I guess, inference for the model itself. And again, typical like cloud products will do it for you. So like Databricks will containerize the model before it deploys it to model serving. Same thing with SageMaker on AWS, as well as Watson on IBM, I'm assuming. But yeah. Cool. Yeah, when we get into next week, we're going to dive into a little bit more of a deep dive in some of these other algorithms. We'll do a formal introduction to tree-based algorithms, as well as other algorithms you may have heard during the lecture today, including support vector machines, KNN, as well as some unsupervised algorithms such as k-mean clustering. And then finally, we'll end kind of with that example of productionalization and what it means to kind of deploy a model. And again, that'll also be kind of brought into weeks 9 and 10. I think week 9 will also go into neural networks and stuff as well. So yeah, week 8 is going to be a really, really busy week, but hopefully this foundation, especially the like life cycle, will give you kind of it won't be all net new material when you get into A1. Yeah, these are all the notebooks you have to do next week. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh my God, 16 notebooks apparently. So yeah, I'll go through them over the week, over Wednesday, Thursday here, and I'll highlight the important ones. But again, don't get caught up in going into depth in any of these, um, unless I like highlight some of them specifically. And I would focus on being experts in supervised machine learning, so anything that goes into classification, the other exotic models such as SVM and KNN, and then the evaluating models. And then finally the keynote, which is going to be building the rainfall model end to end. That's going to be an important one. If you skim through the unsupervised stuff, like that's fine. There's not going to be any unsupervised stuff on weeks 9 or week 10 for the capstone project. And again, in terms of importance, it's definitely supervised ML, then unsupervised ML, and then reinforcement learning. But definitely take the focus on supervised first. All right, I'm 10 minutes late to my next meeting, but this has been fun. I will go through the chat. Let me go through the chat now. Confusion Matrix would be a great band name. Terminology. Yeah, linear regression is machine learning. Yeah, yes. Yeah, it's silly because yeah, you've got your pure statisticians out there, which like go into the linear regression side of things. And the way that machine learning is defined, linear regression is machine learning because we're using a machine to identify patterns and output an algorithm. And typically, I think that machine learning was more focused on like random forests and neural networks and things until people like again realized that the linear models should be treated as that baseline foundation. You should usually be doing a linear model first and then compare your neural network to it because why choose a more complicated and computationally taxing algorithm when a linear model does fine? So I feel like that was kind of the, oh, let's loop linear models back in this idea of machine learning. So again, like, even though you can do it with a paper and pencil, it technically is still machine learning. Statistical techniques are also part of AI. Yeah, again, like to me, this is like the way that the industry's just gone kind of nuts. It's just like anything around mathematics or statistics, or even if you're just doing like an ad hoc white paper, it's all AI powered these days, and it's all especially ML. It's so funny. I literally have customers that are like, yeah, we compete with ML, and it's like, yeah, they have a line of best fit on their Excel chart, and it's like, okay, I guess you're competing with machine learning. Again, I think it's an industry thing. Everything that's remotely predictive is now roped into AI and machine learning. But again, like AI doesn't always have to be predictive, and some statistical techniques like aren't really AI if you really kind of like dig down on it. No one's gonna get mad at you if you say that like linear regression is not AI.
Rebranding.
Scaling, yeah, it's
Rebranding.
branding. It's branding. Scaling
Like,
normalization.
is it cloud computing or is it just running on a server somewhere?
Yeah, hold on. I gotta like bounce here. So let me just finish this up. Scaling and normalization. Typically, if you did that in your stats classes, it would be roped back into the assumptions of linear modeling. I think we talked about this in week 5, that there is assumptions of linear modeling that is not necessarily like it is taught in stats classes, but they may not have taught you how to solve it. So I did some of this in my stat classes. I definitely did scaling. So. Yeah, but getting rid of multicollinearity is a big one. So when we do PCA, it's really funny because PCA, when I did my stats undergrads and made masters, it's like PCA is a statistical technique, but now it's like an unsupervised machine learning technique, and it's like no, it's not. PCA is 100% statistics and mathematics, but now it's again been roped into this like pre-processing machine learning stuff. So again, there's a lot of weird overlap and rebranding of it. Um. I think that's mostly all that I want to go over. All right, I need to hop here. Yeah, so yeah. This Karen still has to call out. What I've realized IBM does is that like it keeps your notebook in like your file explorer of however you ran this in your own environment in your own life. So all that stuff that I added at the end, it was just in my last lecture when I taught this class,
Okay.
I added all that code in and it didn't, even if you click, I tried to do this, even if you
Okay,
try to like
okay, that makes
reset.
sense. I thought I got an inferior
Yeah,
copy.
if you hit reset lab, this button doesn't do anything. I thought it would reset and clear out all my old lecture notes, but it doesn't. So either way, that's why your notebook looks different than mine because I live coded some of mine and you probably still have the original lab.
Yeah.
Same with the
And
students.
I added that stuff myself, but I noticed that it stopped at like log loss.
Yeah. All right, good stuff, guys. I will see you all next week.
I'm
Don't be
not
strangers in the forums, especially if you have questions with any of the terminology or things in any of my lecture notes, GitHub, or live sessions. Happy to kind of talk about this stuff, and especially if you're putting it in real world use cases.
I
Call out anything on the quiz because I obviously didn't have time to do the quiz here. But I
just
really have to go. So, Karen, I'm
you
going to
can go,
pass over
but
to
I
you
was
to close this out.
throwing out an idea as far as naming things. I mean, biology encompasses medicine. So, do we call it biology or do we call it medicine?
Yeah. Anyway, I need to also
Yeah. I was just thinking of that. It's like, well,
uh,
we often put the same things into different boxes, depending
yeah,
on
that's true.
your
Yeah.
interests. So
Rebranding, yeah.
nothing really that new.
No. Have a good one. Enjoy.
Okay,
Bye.
bye.